Welcome to Lab 4. Lab 4 is going to deal with another bsci topic, specifically multicast routing. Multicast can really help us out because it gives us the best of a couple of different worlds. It gives us the best of unicast as well as the best of broadcast. For example, let's say that we had a video server and we needed to send this video stream out to maybe 20 different clients in our network. If we were using unicast, we would have to send that stream 20 different times, one time to each of the recipients. However, if we were using broadcast, we would only have to send the transmission once. However, it would go everywhere, possibly to PCs that didn't want to receive the information. Everywhere in this broadcast domain. That's not a good solution either. With multicast, we could send the traffic out one time, and it only goes to the PCs, the recipients, that want to receive the traffic. We're going to begin this lab with a bit of review. We want to take a look at a couple of different modes of operation that multicast can use. We want to review the multicast theories surrounding dense mode operation and sparse mode operation. Then we want to take a look at the syntax to enable multicast on our routers, what we do globally and what we do on an interface by interface basis. Then we will verify our configurations. After we do our verification, we're going to see a trick that we can use to help us in our initial deployment of multicast. As we're initially setting this up, we may not have a PC that wants to join a multicast group right now. After all, we're just setting it up to begin with. What we can do, we can give a command that's going to convince a router interface that it wants to join this multicast group. It wants to receive traffic that's being sent out to this special multicast address. And let me remind you that a multicast address, that is a Class D address. When a source server sends traffic out to a Class D address, it's sending it out to a multicast group. And different recipients, different PCs as an example, can join this group. After we set this up, we want to then take a look at how we can configure a rendezvous point. A rendezvous point is going to allow us to have a more efficient distribution of the multicast packets in our topology. We'll take a look at why a rendezvous point is needed and how we can configure a rendezvous point. But for now, let's begin our discussion with a review of a couple of different multicast modes of operation. First of all is dense mode. With dense mode operation, let's say that this multicast source on the screen is wanting to send traffic out to the network. It's going to send traffic to the attached router R2, and here's the mentality of router R2. Router R2 just assumes that everyone in the whole network would surely want to receive traffic from this multicast source. So router R2, it floods this traffic out of all of its other multicast-enabled interfaces. It sends it over to router R1 and R4. Fortunately for R1, it does have a multicast group member attached, a PC that wants to receive traffic for that group. So as R1 receives this traffic, it will start to flood the traffic out of all of its multicast-enabled interfaces. It will send it over to that multicast group member, but it also sends it to router R3. And R4 is also sending the multicast traffic to R3. If you look at the topology, you quickly realize that routers R3 and R4, they do not have attached group members. They have no need to receive this multicast traffic. So what do? They don't want to receive this unneeded traffic, so what they do is they send prune messages back upstream to say, please prune me off of this tree. I no longer want to receive multicast traffic destined for this group. At this point, we have a nice steady state, it appears. The multicast source goes into router R2. R2 sends the traffic over to router R1, and router R1 is sending it out to our multicast group member. This behavior we just described is called the flood and prune behavior. We flooded the traffic everywhere throughout the topology, and then routers that didn't need that traffic, they pruned off their branches from the multicast distribution tree. But here's what a lot of people don't realize about this flood and prune behavior. By default, it happens every 3 minutes. Every 3 minutes we have to go through this flooding and pruning behavior. Not a big deal possibly on a small network like we see on screen, but if we had dozens or hundreds of routers in our topology, every 3 minutes, flooding this traffic throughout our network, that could seriously impact the performance of our network. What's a better solution? A better solution is to use Sparse Mode. Let's say that right now we have a Sparse Mode multicast network configured. And our multicast source, it is sending multicast traffic out to router R2, but at this point, no one wants to receive that traffic. Something else I'd like to point out about a Sparse Mode network is that it has a special router called a rendezvous point, or we call it an RP for short. In this case, router R4 is acting as that rendezvous point. Rendezvous points act as a single point that all the other routers can point back to in order to receive traffic for this multicast group. Instead of creating a source distribution tree, as we did with a dense mode topology, where every router that wants to receive traffic, it has its own individual path up to the multicast source router. With a shared tree that Sparse Mode uses, everyone can simply point back to or receive traffic from the rendezvous point, and the rendezvous point can point back to that source multicast router. Well, let's say that this PC that we see on the left-hand side of the screen, let's say that it suddenly does want to start receiving traffic for this multicast group. It sends an IGMP join message to its router, router R1. IGMP, that's the Internet Group Management Protocol. R1 says, it looks like one of my clients wants to receive traffic for this multicast group. Let me let the rendezvous point know about that. And R1 forwards this message over to router R3. R3 forwards it to the rendezvous point, router R4. And router R4 says, it looks like we have a client that wants to receive traffic for this multicast group. Let me speak to the multicast source router and tell it to start sending the rendezvous point, that traffic. So we communicate with router R2, and router R2 begins to send that multicast traffic down to our rendezvous point, down to router R4. And router R4 forwards it back over to router R3, which forwards it back up to router R1, which finally forwards it out to our multicast group member. At this point, we have avoided that flood and prune behavior. However, if we look at the topology, you might argue that we are not using an optimal path right now, and I would agree. We're going from R2 to R4 to R3 to R1 instead of just going directly from R2 to R1. Well, here is the great news about Sparse Mode on Cisco routers. It does it by default. A lot of people don't know about this feature. We're going to do something called SPT switchover, shortest path tree switchover. As soon as R1 receives that first multicast packet, it is going to determine that, it looks like I need to form a shortest path tree with router R2. Router R2 can send traffic directly to router R1. We can prune off that branch of the tree that goes up to the rendezvous point. So we tell R2, hey, would you start sending me this traffic directly? And R2 says, sure, we can do that. And R2 starts to send traffic directly to R1 instead of going through the rendezvous point. And then R1 sends the traffic out to the multicast group member. We end up with the final steady state that we did in the dense mode description we just went through. However, we avoided that initial flood and prune behavior, and we're also going to be avoiding that flood and prune behavior that happens by default every 3 minutes in our network. So we're going to tend to use Sparse Mode in our configuration. Let's take a look at our specific topology that we're going to be working with. We have a multicast source. It has an IP address of 192.168.0.25. It's going to be sending traffic out to the multicast group 239.1.1.1. And notice that first octet. Notice the 239. Remember when you were first studying about IP addressing and you learned about different private address spaces in the IP address ranges? One for Class A, one for Class B, and one for Class C. Well, here's a Class D private address space to be used inside an organization. If a multicast IP address begins with 239, that's meant for internal use, and it's always a destination address. And we have a client attached to gigabit 0/3 on router R1 that is going to want to receive traffic for this multicast source. However, as we initially set this up, we don't physically have a client running an application that's asking for that traffic. To make sure that our configuration works before we actually turn on the clients, we need to synthetically create a client. We can do that. I'll show you a command that we can issue on gigabit 0/3 on router R1 to make that interface join this multicast group of 239.1.1.1. Here's the syntax we'll use to set all this up. We're going to say in global configuration mode on all of our routers, IP multicast-routing. That is globally going to enable multicast routing on our router. Then we go into interface configuration mode for the interfaces that we want to be participating in multicast, and we will say IP PIM sparse-dense-mode. What this is going to do for us, this is going to tell those interfaces to run in sparse mode if a rendezvous point is available, and in dense mode if a rendezvous point is not available. And we're using a PIM, PIM, that's Protocol Independent Multicast, as our multicast routing protocol. This allows us to form multicast distribution trees regardless of the underlying unicast routing protocol. Let's go out to the routers now and see how to set this up. Out on router R1, let's go through those steps we just discussed. Let's go into global configuration mode. And from global configuration mode, let's globally enable multicast routing. Then let's go into our three interfaces that we want to enable multicast routing on and say IP PIM sparse-dense-mode. Let's do that for gigabit 0/1, 0/2, and also 0/3. At this point, I think we're done. On router R1, we have multicast routing successfully set up on router R1. Let's now move over to router R2 and set it up there as well. By the way, router R2, that's the router that is directly connected to our multicast source. On router R2, in global configuration mode, once again, let's say IP multicast-routing. Then we go into each of our interfaces. We have three interfaces we're interested in. We'll say interface fast Ethernet 0/0, and we'll say IP PIM sparse-dense-mode. We do the same thing for interface serial 0/0. By the way, we got a PIM message. It looks like we formed a PIM neighborship. That's good to know. Interface 0/0, we're going to say IP PIM sparse dense mode as well. And finally, fast Ethernet 0/1. 0/1, let's go in and set up IP PIM sparse dense mode for that interface as well. And I think we're now done on router R2. We've done our initial configuration on router R2. Let's now move over to router R3 and do the same thing. Over on router R3, let's get into global configuration mode. Set up multicast routing globally. Then get into interface serial 0 and say IP PIM sparse-dense-mode. Run in sparse mode if a rendezvous point is available, and in dense mode if a rendezvous point is not available. We'll do the same thing for interface Ethernet 0. We'll set up sparse dense mode, and we have one more router to go. We now need to go over to router R4 and do the same thing one more time. On router R4, let's get into global configuration mode and say IP multicast-routing, and we go into interface serial 0, and we'll say IP PIM sparse-dense-mode, and we do the same thing for interface serial 1. At this point, I think we've done our initial multicast configuration. We have enabled multicast on all four of our routers. We've gone into all of the interfaces, and we've said those interfaces should be using a PIM sparse dense mode. And by the way, PIM, that stands for Protocol Independent Multicast. It simply means we're going to run multicast independently of whatever the underlying unicast routing protocol is. Whether we're using RIP or OSPF or EIGRP, as I am in this case, doesn't matter. We're independent of the underlying unicast routing protocol. On router R1, let's issue a couple of show commands to verify our configuration. Let's do a show IP PIM interface to see which interfaces have PIM enabled. It looks like we have enabled PIM for gigabit 0/1, 0/2, as well as 0/3. We're using PIM version 2, and we're running in sparse dense mode. If I want to see my PIM neighbors, I can say show IP PIM neighbor. And it tells me the neighboring routers that are also running PIM. In this case, it's pointing over to routers R2 and R3. There's another command I'd like you to know about, and it's the show IP mroute command. If we do a show IP mroute, we have something here called a star comma G entry. You see this star comma 224.0.1.40? That's a star comma G route entry in our multicast routing table. The star represents the source. And if we have a star acting as a wildcard, we're saying we do not know nor do we care who the source is. Regardless of who the source is, we have a route going to the destination multicast group address of 224.0.1.40. By the way, that is not a multicast group that we have set up. That's there by default on Cisco routers. What it's used for is to automatically discover a rendezvous point if we have auto discovery set up. However, that's not what we're going to be doing in our situation. We are, later in this lab, going to set up a static configuration to point out to our rendezvous point. Let's now go over to router R2. And remember that router R2, that's the router that is physically connected to our multicast source. Let's see if anything looks different from the perspective of that router. On router R2, let's issue the show IP PIM interface command. We have 3 interfaces enabled for PIM version 2 running in sparse dense mode. Interesting. If I do a show IP PIM neighbor, we see that we have a couple of neighbors. And we see how we can reach those neighbors, off of what interface can we use to reach those neighbors. You're going to notice something different, though, when I do a show IP mroute. If we do a show IP mroute, it looks like we have more activity going on here than we did earlier. Look at this. First of all, let me direct your attention to this S, G entry. And S, G is where we do have the IP address of the source, the multicast source IP address, as well as the G, the group address, which is 239.1.1.1. You see, I have a multicast source plugged into Fast Ethernet 0/0, and its IP address, the IP address of that source is 192.168.0.25. And we can see that we're coming into the router from this source by taking a look at this incoming interface entry. Notice we're coming in on Fast Ethernet 0/0, and then I'm going out to the rest of the world using interfaces serial 0/0 and Fast Ethernet 0/1. These are part of our OIL, the outgoing interface list. We call it OIL, OIL for short. This is an S, G entry, and for every S, G entry, we have an accompanying star, G entry. So there's also a star, G entry for the group 239.1.1.1. We also have the group 224.0.1.40 that we talked about earlier. That's used for auto RP. And we have something we haven't seen yet. On this particular version of the iOS that I'm running on this router, this is iOS 12.4, we have another multicast group number of 239.255.255.254. This is used by the Multicast Address Dynamic Client Allocation Protocol. That's abbreviated MADCAP. We call it MADCAP for short. What MADCAP does, that lets a client request an IP address from one or more multicast address allocation servers, and we call these servers MADCAP servers. But most significantly, what I want you to take from this output is this S, G entry. We see the source, and we see the multicast group number. At this point, let's continue our journey around our routers, verifying our configuration. Next up, we want to go over to router R3. Over on router R3, we'll issue the show IP PIM interface command. We have 2 interfaces configured for PIM. If we do a show IP PIM neighbor command, we see that we have a couple of neighbors as well. And if we do a show IP mroute, well, this router only knows about that auto RP, that well-known multicast group address, and we would see similar results if we gave this command on R4. Router R4, it's not connected to any sort of multicast host. It is not connected to a multicast recipient. I'm expecting to see the same thing. Let's do a show IP PIM interface, and sure enough, we have a couple of interfaces configured for PIM, and a show IP PIM neighbor reveals that we have a couple of PIM neighbors. At this point, we have now configured multicast. We've verified that multicast configuration on all of the routers, but we don't have any multicast clients that are actually members of the 239.1.1.1 group. Here's what we can do. Let's synthetically create a multicast group member. We can go over to router R1. Let's go over to router R1 and tell that router that it has a multicast client attached to interface gigabit 0/3. In this case, gigabit 0/3 will act as that client. Over on router R1, let's go into interface configuration mode for interface gigabit 0/3, and here's a command that we can use to make this interface join this group. You see right now, when that multicast server is sending traffic out to 239.1.1.1, there are no members of that group. We cannot ping 239.1.1.1 right now. Nobody belongs to that group. We're going to now make this interface join that multicast group. Here's how we do that. We can say IP IGMP, that's the Internet Group Management Protocol, IP IGMP join -group followed by the IP address of that group. And that group IP address is 239.1.1.1. We've now joined that group. Let's do this. Let's now go back and visit one of our other routers. Let's specifically go back to router R3. Let's get moved over to router R3. And again, R3 is not connected to a multicast source. R3 is not connected to a multicast recipient. And from router R3, let's see what the IP multicast routing table looks like right now. We say show IP mroute. Right now we just know about this auto RP multicast group number, but let's do this. Let's now ping. Let's do a ping over to that multicast group IP address, 239.1.1.1. This will create a distribution tree. It looks like we can reach that group, and we received 2 replies. We received 1 reply from R1's gigabit 0/2 interface, and we received a reply from R1's gigabit 0/1 interface. Let's now take another look at our multicast routing table. We do another show IP mroute. Now we have knowledge about how to get to IP address, to the multicast group IP address specifically, 239.1.1.1. We're now able to reach that multicast group address. And notice we also now have an S(G) entry. The S is 172.16.4.1. That is our serial 0 interface. We are saying that traffic coming into serial 0 can be forwarded to 239.1.1.1 by going out interface Ethernet 0. That's pointing up to R1. That's pointing up to the router that has this interface that is a member of the multicast group. Unfortunately, with our current configuration, we're running in dense mode. We do not have a rendezvous point. Remember, in dense mode, the router connected to the multicast source, it floods that multicast traffic throughout our topology. And other routers that don't want that multicast traffic, they have to send upstream prune messages to stop receiving that traffic. And this flood and prune behavior happens every 3 minutes by default. Let's get away from that. Let's instead configure this network to run in sparse mode. Let's see how we can do that. If we're running in sparse mode, we need a rendezvous point. Let's say that we want router R4 to be our rendezvous point. What we're going to do, we're going to go to all of our different routers and we're going to point to an IP address on router R4. We're going to declare that R4 is our rendezvous point. Let's go out and see the syntax that we're going to use to set this up. We're going to say in global configuration mode, IP-PIM RP-address followed by the IP address. This is an IP address on router R4 because it's going to be acting as our rendezvous point. Let's go back out and take another look at how to set this up. Let's go over to router R1 so that we can point it statically to a rendezvous point. Over on router R1, which remember does contain interface gigabit 0/3 that's acting as the member of this multicast group, let's go into global configuration mode and say IP PIM RP-address and specify an IP address on router R4. We're going to say 172.16.2.2. After we do this, let's do a show IP route to look at the unicast routing table as opposed to the multicast routing table for just a moment. We need to make sure that we know how to get to that rendezvous point's IP address. Do we know how to get to the 172.16.2.0 network? And yes, indeed we do. We happen to be running EIGRP in the background. And remember that PIM is independent of the underlying unicast routing protocol. Let's now do a show IP mroute. In this multicast routing table, we're pointing to an RP address, a rendezvous point address of 172.16.2.2. Let's now go over to router R2 and apply this same configuration. And again, R2 is the router that is attached to our multicast source. We go into global configuration mode, and we're going to say IP PIM RP-address 172.16.2.2. Let's now go do the same thing to router R3. We want all of the routers in our topology to point to this common rendezvous point. On router R3, let's get over into global configuration mode. And we once again say IP PIM RP-address 172.16.2.2. We have one router to go. We need to go over to router R4, the rendezvous point router itself, and issue this command once more. Let's get into global configuration mode first of all, and say IP PIM RP-address 172.16.2.2. We are now done. We have now converted this network from running in dense mode to running in sparse mode. What we've now done, we have told the routers that router R4 is acting as the rendezvous point. So when they want to join this multicast group, instead of sending their join message up to router R2 saying, hey, send me the traffic from that multicast source, instead, we're going to send that join request to the rendezvous point. And the rendezvous point will start to forward us traffic. But after we get that first packet, we realize that this may not be the optimal path, and we can do SPT switchover, shortest path tree switchover, where we can form a direct path with router R2, the most efficient path with router R2. Let's review where we've been here in this lab. We started out this lab by discussing some of the benefits of multicast routing. And we discussed a couple of different modes of operation for a multicast network. Two different ways that multicast traffic could flow through the network. Specifically, we talked about dense mode operation and sparse mode operation. We saw the syntax to enable multicast on our routers, as well as our interfaces, and how to verify our PIM interfaces and verify our PIM neighbors, and take a look at our multicast routing information. We saw how to make an interface on our router join a multicast group, and then to make our configuration a bit more efficient, we saw how we could create a rendezvous point. And by creating a rendezvous point, we could start to operate not in dense mode, but in sparse mode, making the flow of multicast traffic throughout our topology much more efficient. We're avoiding that every 3-minute flood and prune behavior that we had in the dense mode operation. That concludes lab number 4, configuring multicast.